Okay, let's go. Going to start by setting some stuff up in the scene, just to have something to work with. First, we're going to clear the skybox to a solid color, and I'm just going to make it black. Keep things more subdued. I'm also going to rename the scene to something different. I'm going to call it main, because that's the pro thing to do, and delete the sample scene. That way we have a scene called main, which is a bit nicer. Oh yeah, one other thing I'm going to do real quick is I'm going to go ahead and create a Git repo for it. So what did I call it? Particle life. Let's go ahead and go and get a git ignore. Unity, Windows, VS Code. Let's try to just code. And Mac OS, because I might finish this project on my laptop. Okay, so now git status. We've got the VS Code. Wait, we should be picking up the VS Code. Let's go ahead and add. Wait, it's right there. Okay, good. Git add dot git commit add empty Unity projects. Okay, so first thing I need to do is so if you've seen the description below, what we're doing is we're making particle life. The concept of particle life is using a very simple set of rules to create sort of very interesting dynamic behaviors. And so the way it works is there are particles, which are literally just points in space. So the original is 2D space, but we're going to be doing a 3D to see if anything interesting comes out of that. And there are different families of particles, so they could be different colors, for instance. And the way it works is each family basically has rules towards how it reacts to every other family. So it can either be attracted by those other families or repelled. And there's a curve over what distance at which they're able to be attracted or repelled. So by using that, we eventually get systems where maybe there's one particle that's repelled by this one, but this one's attracted by that one, so it would sort of move towards. Or we could have a system where maybe there's particles that are all sort of attracted to one, but they're sort of repelled from each other, so they sort of create a bubble around that one, for instance. Stuff like that might happen. And then because they're sort of pushing and pulling at each other, this creates sort of acceleration. So another thing we do is we just apply friction to them to sort of slow the system down and keep it all nice and under control. And what I'm going to do is I'm going to randomize the initial conditions and see if interesting things happen. And so by initial conditions, it's basically how many particles there are, well, how many families, how many particles, and what the rules are, what each family wants to do towards other families. So what I'm going to do is just create a particle script straight away. Particle. And so here's our script, and the first thing we need to go ahead and do is create a public struct family, which basically should hold it's a color, so let's go ahead and add a public color. So each family has its own color. We'll randomize those. And then we also want a public array of family and rules. So basically we're going to have a struct for rules as well. Public struct rule. And so a rule is a link between a family and like what behavior we want. So each rule has a public family, and then the rule is going to be basically a value like attraction or repulsion value. So it's just going to be attraction, and repulsion is going to be negative attraction. So public float attraction, and then we got a minimum range and a maximum range. So public float minimum, so min range, and public float max range. Should I model that as a minimum range or the maximum range, or a like range and then like a range spread? I'm gonna model it like that. So range, so the range at which we apply the rule, and then public float range spread, and that basically tells us like how much beyond and behind that range we apply the range still. Okay, so each family has a list of rules, which is basically how it behaves towards particles of other families. So that's going to be a particle rule array rules. And that's all they need for now right now. And so each particle, so a particle itself belongs to a family. So public family. And it also, that might actually be an int, which might be its an index towards the family, because there's going to be basically there's going to be like a global sort of list of families, and each particle is going to be a member of one of those families. So yeah, that's how we're going to model this. So I'm going to go public family array, so like each family, and we're going to call it families. And this one's going to be static. This is going to be a public static array of families. And so we don't have a public family, we have a public int family. Yeah, actually, I'm going to hide that. I'm going to do a trick straight away just to simplify my code later on. Public int family index. Sorry, not public int, and instead there's going to be a public family, and this is going to be a property get, and it's basically just going to return families family index. So what that is a property in Unity. So basically, like this becomes like this sort of magic value, and if I try to get it, it will. So if I try to read that value, it will go ahead and look up what family I belong to by looking at my index and seeing where I am in that array. Okay, so the next thing to do, so I got my own family, and I'm going to have my velocity as well. That's going to be a public vector3 velocity. So that's like how fast this particle is going. So anything that doesn't have static in front of in this class is going to be like specific to one instance of like to each particle. So each particle has its own velocity and its own sort of index, so it knows which family it's a part of, and so that way it knows what rules to apply. This could actually be a dictionary of families rule. Yeah, this is going to be a dictionary. That's exactly what it's going to be. Dictionary family rule. That way we can look up directly for each family what its rule is. Cool, cool, cool. So to do the lookups really quick, what I can do now is I can create myself a public rule. Actually, that should be public, just internal. Get rule and get another particle P. Wait, is particle something that exists in Unity? I really hope it isn't. That's going to be fine. And what that does is it returns family. So my family rules of P. The family. Oh. Yeah. So that's how I get a rule for a particle. So if I'm a particle, I can look at another particle and see what rule to apply. So in the start, I'm going to real quick check if families is null. So the first particle will create all the families and then initialize from that. We can even do that in the awake. That way it's done before anything starts. Void awake. And so in the awake, what we're going to do is if families is null, we're going to go ahead and create that family thing. So the way we're going to do that is we're going to use a int family count equals, let's hard code this for now. I'm going to go like 4 families, and what's going to be the range, and we're going to go ahead and just add some like values for this. So float attraction, max attraction equals, let's just say 1. I have no idea what the value is going to be. Actually, that's going to be closer to a, I say I have no idea, but I do have a little bit of an idea. This is going to be closer to like a 10. So float at max attraction, float, so min range and max range. So here we do want a min range and max range. Min range is going to be like, say, 2, and float max range is going to be like 10. I don't know. I actually don't know for that one. And then the range spread, so that's going to be like float min spread. Ooh, it should probably be proportional to whatever the ranges are. So let's just say it's somewhere between, okay, yeah, float min spread is going to be like 0.25, so it's going to be a quarter of whatever the range is. And the max is going to be, well, 1, because that would mean that the range goes all the way down to like us. Float max spread is going to be equal to 1. Cool. And oh yeah, we need to create the families as well. So families equals new family array with family count members. Cool. And now just do a quick for loop for int I equals 0, I less than family count, I plus plus. What am I doing? Oh yeah, I'm creating families, and then I have to create the rules for all of the families. Ooh. Oh yeah, so I'm going to create all the families, and then I'm going to iterate over each family and create all of their rules. That's how I'm going to do that. because I can't create all the rules until I have all of the families. So the rules array, this is going to have to be created afterwards. That's fine, I hope. Oh yeah, no, it's fine. I can create it and then I can insert afterwards. Okay, that's cool. So family, familam, familam.color equals random color HSV. And we're going to go, what I got? Human, hue max. Can I just go like any hue? And I have to like say which my min and max hues. So what is it? Human, hue max, and I'm going to want to like push up the saturation. So human is going to be 0, hue max is going to be 360. Oh, 0 to 1? 1. Saturation, I'm going to go like fairly high saturations. So it's going to be like 0.7 to 1. And the value is going to be always maximum. So 1, 1. And this one needs an F. Cool. So some nice bright colors here. Familam color is, so that's that. And then the rules need to be created as well. Familam rules equals new dictionary of family and rule. That's cool. I've got something wrong with my indentation. Let's go ahead and fix that. Why is it adding this sort of weird space here? Go, go, go. Go away, go away. Oh, is it the whole thing? Yeah, the whole thing's fully indented. Bam, bam. You guys go here, and you go here. Cool. So, now that I have all that, I can iterate all over the families again, and then give them all their rules. So, where am I right now? So this is outside of this loop. Oh, the loop is here. Okay, and these are necessary for the rules. So now we're going to create the rules. So for each family, familam in families, we're going to need to add a rule for each other family. So we need for each, and this time we're just going to go F to keep it nice and simple. Family F in families. So this is a doubly in, like, we're looping over each family, and for each family we need to have a rule for each other family. So that's why we've got these two loops. So familam familam rules add, and so the key is going to be F, and the value is going to be a new rule. So we need to create the rule first. Rule. And it's going to complain because rule hasn't been initialized yet, but we just need to create these values first. Rules don't need a family. Yeah, so just attraction, range, and range spread. So rule attraction equals, so it's going to be either negative to maximum attraction, so that's random range, negative max attraction to max attraction. Rule minimum range, sorry, rule range is going to be somewhere between minimum and max range, so random range, min range, max range. And then the spread is going to be whatever that range is multiplied by somewhere between min and max spread. So rule spread, range spread equals random range min spread, max spread, and that is going to be multiplied. You know what, let's, yeah, go ahead, let's just pre-multiply it. Rule range. Cool, and we just add that rule in for the family. So each family now has, so each family here in Familam has a new rule for each family, and we just create that rule, which is just a set of random numbers which are useful for deciding where things move. Cool, cool, cool. So that's done in the awake of each particle, but it's only done if the family's array is null. So the first particle that like wakes up will create all of the families, do all of that stuff, and then the other particles will just ignore that and just keep going. And then in the start, each particle is just going to pick one of the families at random. And the way we do that is simply go family index equals random range again. And so the minimum is 0 and the maximum is families.length. So some index in the family index. Cool. What I'm going to do for now is I'm just going to quickly create a couple spheres in Unity, put a material on them, and just make sure that they're all sort of like picking random colors from there. Cool, cool, cool. So let's go ahead and create our first particle. So should we call it a particle here? That gets the particle scripts. And let's go ahead and add a sphere to that. And let's go ahead and create a material just for that. Oh, it's going to be unlit color. Does that work? Yeah, we got colors. Cool. So we're going to go ahead and put that on the sphere. And so the particle velocity isn't supposed to be public. Where is the velocity? There it is. Cool. But it's going to go in its start. It's going to go ahead and find its renderer and just set the color of the material that it's got. Is that magenta because, yeah, because I picked magenta. Okay, I'm gonna take that away because magenta means like buggy material in Unity, so I keep thinking that there's a problem with the material. Okay, so what we do is we go ahead and assign our renderer the color. So for now we're just going to go get component of children, renderer, set color, and a set property, isn't it? Set. And I need to get my material. This is set color, isn't there? Yeah, set color. Set color, so the name is going to be what? Main color? What's it called in the shader? Select shader. It's called underscore color. Okay. And the color is going to be the color of our family. So it's going to be family.color. So if I go ahead and create a whole bunch of these particles, can I see? Yeah, I can see it right there. So I'm just going to create a bunch of these. Control D, one to the left. Control D, another one to the left. Sorry, that's right, actually, isn't it? And then 4, and then let's just create some more, 5, and I wonder if I can do this. I really don't think I can. -1. Nah. Control Z that. Okay, I just want to go ahead and Control D that one. Add a negative. Control that one. Add a negative. Which I haven't met done this one. Control D. Add a negative. Damn, if there were only a way to like write code that would do this for me, huh? That'd be cool. Someday someone will invent this kind of technology, but we're not there yet, are we? Okay, let's go ahead and save the scene, play, and these should all be sort of like random colors. No, they're not. What's our error? Family rules, add a fool. Let's go ahead and just check those. Debug log. Let's log our rules, family rules. Let's go ahead and debug log. Wait, we're not adding families to the... That's what's going. Families of I equals family. Yeah, I create the families, but I don't actually put them in the family array. That's why we got that problem. Okay, this should might be a bit better. Cool. So yeah, apparently we've got like these colors repeating. So we got like red, red, red. We got some blues. We got a green one. Got a couple of oranges. So that's working. And so the first thing I'm going to do, the next thing I'm going to do, you know, I'm going to make it so that they already like spawn. Actually, no, let's finish this. So what they're going to do now is basically each particle is going to look at every other particle in the scene, and if it's in range, it's going to go ahead and sort of apply its attraction or repulsion to itself. Yeah, cool. So this is actually kind of ugly because it means that everything's sort of checking against everything else, but there isn't really a way around that, is there? Not really, no. Okay. So for... Oh no, actually we need to get every other particle, not every other family. So real quick, I'm going to create a particle array as well. Public static particle array. Call it particles. And so families is null, particles is also null. So the last thing we're going to do, actually that can't be an array because I need to know how many particles there are at that point. And right now I'm just inserting them into the scene. So we're going to make that a list, which is fine, I think, here. But we still need to create the list. So we're just going to go ahead and do that as well here. And I'm just going to do it right at the beginning. This should actually be here, I think. Create the object immediately. Oh. Boom, boom. So particles equals new list of particles. Cool. So when particles appear, they also add themselves to the list. Particles add this. There are more elegant ways to do this, but this is not the point of today's exercise. So the next thing they do, so what they do is they look at all the particles, and if they're not looking at themselves, because obviously particles can't sort of push and repel against themselves, they can only do that to other particles, then they sort of do their attraction thing. So just do it real quick. For each particle P in particles, I need to get the rule, so rule equals get rule of P. So that means that gets the rule, my rule for particle P. That's this function we wrote earlier. So basically we're getting our rules and we're looking for the family of the particle that we're questioning. So now that I have that rule, I can decide whether or not it's in range. So if, okay, I need to get the distance first. Float d equals vector 3. And we're actually going to get the square magnitude of the distance. So that's going to be p transform position minus transform position. And that's actually a vector we're going to need. I'm not sure of the direction for that vector yet, which actually doesn't matter because we're doing both pushing and pulling. Actually, it does kind of matter, but for another thing we need later. So I need to look that up real quick. So vector 3, what we're going to call it? V. V is a good name. So hang on. So what we want is the vector that goes from us. We just need to decide a direction. It's going to be from us to them, and this is how we do it every time. If we're at 3, they're at 5. From us to them should be positive 2. So that is 5 minus 2. So it's their position minus our position, which is their position minus our position. Good. So we're going to get the square magnitude of V. We get the square magnitude because it's a little bit more optimal. There are less square roots. And the way we use that next is we go if, so d, the square distance, let's actually call it d2, so we know it's a square distance. If the d2 is more than rule range minus rule range spread, and it's less than rule range plus rule range spread, these need to be squared. I don't know how efficient math power is. Let's pre-mod them. Let's do that real quick. Float min range equals that. Min range multiplied by itself. So we're just squaring them. And then same for this one as well. Float max range multiplied by itself. You know what? Screw it. Let's just use magnitude. And let's stop faffing about with optimizing when things don't need to be optimized yet. Cool. So if we're in range, at that point I need to decide how much I'm pushed towards or pulled away from them. So basically what it's going to be is going to be the attraction multiplied by how far away we're from rule range. So we want it sort of like diminish like that. So the way we do that is going to go float attraction equals rule attraction multiplied by whatever the absolute value of d over rule range divided by, no, both of them. I need to draw a picture. Let's draw a picture. A big pen. Let's draw a picture. So what we're doing is, so this is us here. This is our distance, and this is range. This is like the bottom and the top of the range, and basically we're doing a curve that looks like this. Okay, and so if we're assuming that we're there, we want to be like halfway away because that's about 50%. Okay, this is 1 here, and this is like 0 and 0, so this should be like 0.5-ish. And the reason it's 0.5 is because this distance is half of that. So we have, is yellow even going to show up? Let's just go ahead and pick a, let's go ahead and pick a green. So this here, this distance here, that's D. That's D right there. Rule range is this. Range spread is that, so that's spread. write it out. Because I like writing things. That's the spread. I'm bad at math sometimes. So this is also spread this side as well. And honestly, we don't really care which side it's on right now. But both of these are equal to spread. And so basically I want to know where. Oh, this is the, like, no, distance, that's not distance. Sorry, I'm bad at this. That's distance. Whoops. Can I undo? Yes. That's distance right there. Distance is from here to there. That's range. And what I'm looking for is that much. Haha, I know what value I'm looking for. The value I'm looking for is this one here, which is equal to because it could be positive as well. But basically, okay, it's the difference between, it's the absolute range minus distance. Okay, cool, cool, cool. So that's d minus rule range divided by rule range spread. Cool, cool, cool. That's good. So that's our attraction. And so now we just basically push ourselves or pull ourselves away from, we just apply our attraction as an acceleration. So we just go velocity plus equals v normalized, because we don't, here we just want the direction, multiplied by attraction, and we're just going to integrate that over time. We could do better integration later, like do RK4 or something, but right now we're just going to iterate like that. And then the last thing we do, once we've moved, ooh, yeah, I'm going to do that in a late update. Basically, I want things to like decide how fast they're going to move, and then all move together in the same step. And so in Unity, you can use that, and then you can use late update. So what this does is basically Unity does all the updates, and it does all the late updates afterwards. And so in the late update, we're going to go transform position plus equals velocity times time delta time. And another step we need to do is we're going to need to like apply friction, but right now I'm going to not care and just see what happens, because there are lots of other things we need to worry about. So right now we're just going to see what happens with friction, without friction. So these should all sort of fly off and move around. Yeah, because they're all on the same line, they're not actually sort of moving around. So let's just go ahead and sort of like give them a little bit of movement. It doesn't really matter how much. We just need to not be perfectly aligned. And actually, right now we're doing a 2D version because since they're all got like a z of 0, they should sort of stay in the xy plane, which is interesting. It doesn't really matter what the initial conditions are, they just need to not be like all at 0. And now we should get like, there we go. So we're getting like movement happening now. And as I said, they're sort of staying in the xy plane. That's fine. But we're getting, okay, so we're getting the kind of thing I was talking about, right? Where I said that we're going to have like sort of dynamic things happening. So if I sort of follow this one here, and take away play, so now we're sort of following this one as it moves through space. Apparently, so these orange ones like seem to be like interacting with the red ones, which means they're sort of staying clumped together. The blue ones, however, are like, nah, fuck you, and they're sort of running away. So that's interesting. That's super cool, actually. Okay, so the last thing we need to do to just like obey the rules of the game is to go ahead and give them friction. Right now we're editing everything in the code. Like we're just literally just like writing numbers here, so I might as well just write numbers here as well. So the way we do that is we just go velocity. So once we moved, we go velocity minus equals. So the way we apply friction is you just take away velocity times some friction value. So it's going to be times, so minus the velocity times friction, which is going to be, let's just go 1 for now. And then that's also time delta time, because everything sort of integrates over time. So now they should sort of like clump up a bit more, or at least like not fly away at massive speeds. Yeah, so we got this sort of situation where like these ones are trying to like go towards the blue one maybe, and these ones are trying to go towards the green ones. This one's trying to move away from the from these. Looks like that. That's cool. Let me just go ahead and change the music real quick. Actually, I'm done with that for now. Yeah, so as it says on the screen, I didn't ask people if I could play their music on stream, and I don't want to like get in trouble with copyright stuff. So I'm playing music in my headphones. If you want to listen to something else, you go ahead and listen to whatever you want to listen to. And if you want to know what I'm listening to right now, okay, right now I'm listening to this. Wait, where's my, okay, I can go ahead and find chat here. I am listening to this album, and that is Julia Bonda with an album called Black Noir. So that's Julia Bonda, Black Noir. That's what I'm listening to. Okay. Oh, and I can hear my own self here. Cool, cool, cool. Okay, so what I'm going to do now is I'm going to go ahead and instead of put them manually in the line, I'm going to go ahead and create like a spawner. Ah, and the spawner could have could pre-initialize these values for us. And so actually the spawner will do this bit. So we're going to put that in the spawner. So we're just going to go ahead and, oh, hang on, I'm not on the right screen. Okay. So I was saying I got rid of all the particles we had in the scene, and instead I'm going to go ahead and create a spawner, which is going to deal with creating the particles for us, and it's also going to be spawn particles, and it's also going to go ahead and set up the rules of the game for us, so we can do things easier there. So I'm literally just going to move this, move it to spawn particle. Let me go ahead and change the name of that in a minute as well. Yeah, those are also going to move over to the spawn particle thing. And the family and rule system are also going to move over. Okay, and so you need to get rid of this, get rid of that, and then here we go spawn particle dot families. There you go. Cool, cool, cool. That keeps like the behavior of each particle separate from like the global behavior, which is going to be part of this. And so that means that we can put these as parameters now. Yeah. And go ahead and Can I do one of these? Oh yeah. Public. And so we can also like go ahead and like public friction, flip friction, sorry. Which is going to be the value we use down here. Oh wait, it's not going to be like a... okay, it will give the value when it creates a new particle. So public float friction. We can show it in the editor, that's fine. Okay, cool. So now it's the spawn particle system that creates the whole family system. And so it shouldn't do this. Instead it's going to go ahead in the start and go for int I equals 0, I less than public int particle count. Particle p equals I. You know what, we're going to have particle prefab as well. Public particle prefab equals instantiate prefab at p, and this should do more or less the same thing, except we're going to go ahead and add a random position. Yeah, so prefab public float spawn range. I'm going to spawn things in a sphere. What else do we need? Yeah, we're spawning everything in a sphere. Random inside unit sphere times spawn range. No rotation. Cool, cool. Okay, let's go and add some like values here. So for now, I'm just going to create 10 of them, and the spawn range is going to be, say, like 10 units. And another cool thing we can do is we can make the spawn particle, the spawner, essentially sort of follow the particles by calculating like the average position. We'll do that later. Let's do that later. Right now, I want to go ahead and can I just reset? Yeah, reset. And oh yeah, I shouldn't have deleted them immediately. Particle. So a particle has one of these, and it has a sphere. The sphere itself shouldn't have a collider. Let's get rid of that. Why is that in scenes? Shouldn't be in scenes. Neither should that. Okay, and so the sphere has this material. Cool. And we can go ahead and create a prefab of that. Delete it. And so the spawner has that as a prefab. Look. Wrong script. Particle script. Cool. The spawner has that as a prefab. Cool, yeah. So this should create 10 particles within a range of 10. And family count should also be a parameter. So it's going to create 4 families and then spawn 10 particles total. You know what, if there's 4 families, let's create 40 particles. That way it should be roughly 10 of each. Let's see what happens. That's cool. So we got something happening. See what happens if I create like more families, like 10 families, 40 particles each. Yeah, we're kind of getting towards like it's the same idea. So like if I set myself in like one of these views, yeah, we're sort of missing a dimension, so we don't see the whole thing. But like that group is sort of broken off and gone in its own direction. So in 3D, obviously, we're going to need a lot more particles before things get interesting. So let's just see, let's just do like a real quick stress test, 400 particles, and I'm just going to give them a bit more range. I'm going to give them like a range of like 30 maybe, and then go ahead and see what that does. It lags out my computer, and so I'm going to start dropping frames. 400 particles is too much. That's not a great thing, because that means we're going to be very limited, aren't we? If I'm just going to reduce these values here. Min range is going to be 1, max range is going to be 5. And let's go ahead and put like let's keep that there. Oh no, they're not touching each other anymore. Let's give them smaller range again. That's cool, there's stuff going on now. That's actually really cool. So actually, if I want lots of particles the way I want them, I'm probably going to have to learn Unity's like entity component system. That's actually really cool, I like that movement. I like that, it's pretty cool. Cool, cool, cool. And so the last thing that's actually in the original version is when two particles get too close, no matter how attracted they are to each other, they will repel. So we're just going to go ahead and add that real quick. Public float radius. And so, why is everything bad now? I recreated the script in there. That's it. That's what I did. This is the one I want to be editing. That's fine. Okay. Float radius. And what we're going to do as well is, so yeah, friction radius here. And we need to go ahead and give each particle, when we spawn it, its radius and friction. P radius equals radius, P friction equals friction. That way these are like initialized on creation. And so the radius, basically what that's going to do is going to override this instead. So first we do is if d is lower than radius, at that point we do a repulsion thing, and then it's only if that's false that we do this, else if that. So at this point we have that was weird. Float. So we said that the v was the vector from us to them. So we want the opposite. So there's going to be we're just going to call it push equals so the push power is basically d divided by radius. No, 1 over d divided by radius. 1 minus d divided by radius. So it's going to be like 1 when we're at 0, and it's going to be 0 when we're at the radius. That's the push power. Yeah. Call it push power. Push power. So push is that times push power. So that's how like hard it's going to push. And the way we apply it is we go velocity minus equals v normalized times push, and that should like push things away from each other. And the push power is also going to be a spawn particle parameter. Push power, let's give it a power of like 100. Basically a lot. And so when we create new particles, P push power equals that push power. That might be a bit much, but we'll see what happens in the editor. Okay, so when I go play, now if particles bump into each other, they should sort of repel each other a bit harder. Yeah, you can see these sort of like bumping into each other over here. Most of them sort of like ignoring each other though. So what we can do is we can go ahead and like maybe sort of increase that max range. Yeah, so the min range can be like nice and small, but the max range can be huge. Like say, well, how far are they spawning at 10? Let's go ahead and do a max range of 20. Yeah, okay. Now things are sort of happening. Yeah, and they're repelling too hard, so I think I put push power way too high. And we can also give them a bit more friction. But so now it's a lot of tweaking. We're also going to need to optimize that square magnitude thing, because if things aren't in range of each other, then they shouldn't be sort of pushing and pulling on each other either. Or they shouldn't like even need to calculate their range and stuff. Oh, I like this. Like this is sort of like a sphere around that green huddle there. And the whole thing is sort of moving around. So if there are fewer families, let's go ahead and put it back down to 4 again and see what happens. So basically each time I play now, like a different thing is going to happen, and it may or may not be interesting. Yeah, purple and yellow create this sort of like spaceship thing, and pinks and reds don't want to be a part of that. Actually, the reds are sort of like following around, which is interesting. It's creating like a snake sort of thing. That's cool. Sort of following each other around over here. That's cool. Okay, so I'm happy with that. Like, a lot of things happened and came out quite alright. Now I'm going to have to like find a way to make the camera sort of move itself into an interesting position. And I also want to see what the what my maximum particle, yeah, so I'm already getting like frame rate drops there. 150. Oh. Bit of a weird one. Oh, so these green ones are like, look at this. These green ones are all trying to get away, or at least stay at that range. But then there's like this sort of like captured blob of green ones in the middle, and they can't get out. And they have these sort of like 3 shells around them. That's cool. There's lots of interesting behaviors that come out of this, isn't there? Oh wow, a circle. So it's like creating like a... wonder why that's happening. This is cool. Wait, I can set the grid now? Oh, this is new. Cool. I can also hide the skybox, so I don't want to see that. I can literally just hide it. You can hide things in the scene now? Lots of new stuff in... I haven't used this version of Unity yet, already. Oh, nice big spaceship going around. Three thrusters at the back. Okay, so I'd really like to... So now it's going to be a bit of an optimization. So before I touch that, I'm going to go ahead and do a quick git status. Yeah, go ahead and add all of these. Git add, git commit. And I'm just going to call this stuff because I can't be bothered with names right now. Okay, so in spawn particles, so we have this, sorry, in particles, this is basically where a lot of the stuff is going wrong. Magnitude, to get magnitude, basically it has to do a square root. So if we go square magnitude, we get d2, and so we can go d2 minus d2, radius times radius, right? And that gives us the, like, the square root of d2. See, so this is like the kind of optimization that's should get rid of a bunch of square roots. So what we do is we just like take the square magnitude, it's just quicker to calculate, and only do the square root if we're like within radius. And so we need to do the same thing here, but that means we need this squared. So I'm just going to go float little m equals that, and float big M is going to be equal to that. And m equals, so it's just going to multiply by itself, and the same with capital M as well. So we got the square values for those. And so now we can go d2 bigger than little m, and d2 smaller than big M. And at that point, we can square root d at this point here. So that should reduce the number of square roots we're doing. Another thing we could do is, because each particle is the d2, we'll do that in a minute, but basically, like, if these two particles are interacting, once we've calculated the distance one way, we can already calculate it the other way. So what we could do is, if we're inside one of these two cases, so basically where we have to do the square root, we can just go ahead and give it to the other particle, say, oh, by the way, your square root towards me is this much. And sort of maybe store that in an array somewhere. Yeah, we can do that if we need to. We'll see if we need it. Okay, so this should behave the same way, but I think it's just as laggy. You know what, before I try to like optimize too much, let's go ahead and just have a look at the profiler and see what is actually costing so much. Okay, we've got a bunch of frames. Let's go ahead and select one of them. So rendering is okay, I think. Oh, rendering is nothing. So we've got scripts here. We've got a bunch of garbage collection. Oh, is that the for eaches? Okay, can replace that. And then we got, yeah, the scripts, obviously. Can we go ahead and have a look at what's doing that? Player loop, particle update. Yeah, the particle updates the bit's taking a lot of time. Okay, let's get rid of the for eaches. So instead of for each, we're going to go. I wish the for each would work properly, but for int I equals 0, I lower than spawn particles count I plus plus particle p equals spawn particles of I. Like, that's it. Like, the for each should just like compile to this. I don't know why it doesn't, but that should get rid of our garbage collection stuff. Or not. $180,000. Where are we getting 180,000 garbage collection calls? Oh, real quick. If p is different to this, sorry, equal to this, continue. That's a small thing, but we shouldn't be just checking against ourselves. Is get rule. What's causing all that garbage collection? I don't know. Yeah, it's still getting a bunch of garbage collection. Deep profile and call stacks and see if that gives us information. That's annoying. Okay, we've got a few frames. Oh, get rule is taking up like most of the frame? Why? Dictionary lookups are huge. Okay. So, we are actually going to use an array here. Yeah. The rules array is as big as the family count. Because there are as many rules as there are families for each family. Instead of going familam rules add f rule, we're going to need a integer here. So this is going to be an int loop. You know what? It's going to be exactly the same as that one. So the rule for the ith family familam rules of I, familam rules I is equal to rule. Cool. So that's that done. And on the particle side, when we get rules, instead of that, it's actually going to be the family index. Yeah, cool. Damn it, that was it. Okay, let's get rid of the profiler. Damn, it's so much smoother. Let's go to 400, see if that works. Okay, that's a bit laggy, but we can do 250, right? So this actually goes up with the square of the number. The complexity is going to go up with the square of the number. But that's nice that we can get up to 250 quite easily. So the next thing I want to do is have like is basically have the camera sort of detect where interesting things are happening, which I guess would mean sort of measuring sort of density and velocity, sort of like a field of where things are moving and where things are like sort of clumped together, I guess. I don't know. This is cool. I like this. You know what? We're just going to do something real quick, just to make things look really cool. Check this out. So when we do our get component and children renderer, we're actually going to go ahead and get that renderer. So transform renderer. Oh, sorry, yeah, like let's just go like visual. I'm just gonna call it visual. I'm going to go ahead and go renderer rend equals that. Rend material do that, and we're also going to go visual equals rend transform. And so what we're going to do in our late update is what we're going to do is we're going to rotate the renderer so it's pointing in the direction of our velocity, and we're going to sort of scale it depending on what that velocity is. Public float velocity scale. And it's going to go visual rotation equals quaternion look rotation velocity, and then visual dot local scale equals vector 3 dot 1 plus vector 3 up times velocity magnitude times velocity scale. The velocities should be in like the hundreds, so the velocity scale should probably be like a 0.1 or something. Not quite doing what I thought it would do. Not up, forward. Silly Billy. There we go. And things when they move fast, they can sort of like scooch out. That's cool. Nice. Oh, this is going to happen when it's not moving. If velocity magnitude superior to 0, do that thing. Else, and we don't need to do that. Visual local scale equals vector 3, 1. Cool. Wait. I'm used to coding on Mac and the buttons aren't in the same places, so I keep doing this kind of mistake, and it's a bit frustrating. Whoa, they're shooting off into the distance. Okay, so what I'm going to do right now is just going to like let it simulate for a bit and sort of place the camera somewhere where it looks kind of okay. So it's around here. So let's go ahead and put -100 and 0. And that's about the right numbers, yeah. So at least we've got the camera in a position where it starts out in an interesting point. I think that scaling is a little bit much. Reduce it a bit. 0.25 maybe, or 0.25. Scaling is a bit more subtle now. So what I want to be able to do is have the camera sort of figure out where this kind of thing is happening, because this is exciting over there. Like it created like a kind of animal that's sort of gliding through space. Where is it? It's over here, isn't it? That's cool. like that. What happens if there are as many families as there are particles? So it could be multiple particles of the same family, but generally it's going to be a big mess. So there could be families with no members, and yeah, so this just does a mess, isn't it? And like if there are two families, it's going to do something like really sort of like, yeah, something like that. Okay, so sometimes it does something a bit more interesting. Where's the middle of the world? It's over here. I need to create, oh, I can create the spawner. Yeah. So it does do some interesting things, but I think you need like at least 2 or 3 families for something interesting to happen. Okay, I take that back. That's actually pretty cool. Cool, cool, cool. But yeah, we get interesting like properties at like 4 or 5 upwards families. Well, not in this case. And another thing is, should we sort of force families to, sorry, particles to sort of like stay near the center? Either by like giving them like a direct attraction to the center all the time, or maybe like have limits to the world which sort of pushes them back. I think that's going to be an important thing to do. Because like right there, like those just left. They're off. They're not coming back. I wonder what happens if I like reduce the attraction significantly, but also the friction. So things are like a bit more like, yeah, things are looser. And on the other hand, what we can do is we can sort of multiply them instead. So like, go like 100 attraction, but like 20 friction. And what will happen there is, there we go, so like very sort of twitchy movement. Oh, I like that as well, that's cool. Maybe the animal's friction should be like, the particle's friction should be like a function of their attraction. That could be cool. Oh, it's cool if they come back. Oh, wow. Okay, that's cool. Yeah, so interactions between groups, especially with sort of like high frictions, and that's actually where we want things to be. What's the spawn range? Spawn range is 10 and then max range is 20. Let's go ahead and put their spawn range at the same as their max range. Yeah, so there's a few frames where it's sort of just bleh, and then it does interesting things. Okay, and I think the radius might want to be a bit bigger, and the push power just, it's the same. Turn those down a bit, see what happens. damn, I love this. This is like legit really cool. Okay, so okay, I'm just going to commit all that. Turn the light on as well. Where's the light? Okay, git add dot git commit moist. Let's go ahead and make our camera sort of follow the center point of where all the follow particles. So what it's going to do, it's going to try and figure out where the center mass of all the particles are, and sort of follow that. The most basic way to do that. Oh, actually, the camera itself should be following the particles. The anchor should follow the particles. So we're going to put an anchor at the middle of the map. Camera anchor. And attach the camera to that, and give the camera the follow particles script. And so what it's going to do is going to go ahead and look at all the particles. So one of these are cool. Yep, spawn particles. Start off with a neutral vector, vector 3, 0. Pos plus equals spawn particle particles I transform position, and at the end pos gets divided by the number of particles, and we go ahead and put ourselves there. Transform position equals pos. And that should like have the camera anchor sort of sit at wherever the average position of all the particles are. Yeah, so nothing's sort of staying on screen. The problem is if it breaks up into multiple groups, then we won't we'll leave some of them behind. This is cool. There's some cool stuff happening here. I'm going to need to transform this into a screensaver. That's not a very interesting one. I think I really want to transform this so that it uses Unity's new entity component system. I'll do that off stream though, because I have no idea how that works, and so I'll be following tutorials and it's going to be boring. But the main idea is that I kind of want to be able to ramp up the number of particles. And here it's going to be doing like one object for each one, and it's going to be too much. And I think the ECS or the job system or something is supposed to is for this. I vote for the screensaver. Yeah, it's going to need to be more optimal because I think this is eating like resources. Yeah, 40% CPU usage screensaver. let's build this and see what it looks like. New folder, reads. Because I'm assuming built it'll be more efficient because it always is. So like, yeah, if I do screensaverize it, I think what we'll need to do is find some way of make it detect whether it's an interesting one and go to the next one. Yeah, I actually need it to just reset every now and then and sort of give us a new family. What would be super cool is to have like a thing where each family has like a seed family, like so basically a family that it creates. Maybe it could be like the next one on the list. That way, like all of the families get created, and basically fill up the world with like uninitialized particles. And whenever a particle that's part of a family sort of gets near to one, this uninitialized particle basically like takes on a family and sort of adds itself to the simulation. And so we could sort of like have like loads of particles out in space and sort of add them as we go along. But then also, like if a particle hasn't moved much, or if it's like, I don't know, like find some way of like having like food or something in space, and so if things don't eat for long enough, then eventually the particle dies. I don't know, something like that. That'd be cool. I don't know. Coming up with ideas for these things sometimes can be a bit rough. I do like this though. I need an escape button to quit the game. Where did the game put itself? It's going to be in this PC. See, oh man, I need to empty some space. Particle life, particle life. I do feel like it runs a little bit nicer in the when it's built. Let's see if I can just like bump it up to 400 and create a build with 400 in there. Let's see what that does. Yes, it runs better in build as it does in the editor. We're not at 60 frames a second anymore, but it is running faster than it was when I was running it outside of editor mode. So running it in editor mode. Like 400 particles does like work here. Oh wow. Oh, look at that. And then, so we got like these two little animals, and then they sort of like interact with each other. So this is the kind of thing that the particle life system does. What's the original name? The original name is something like clusters. And so it like creates these sort of like animals of different families sort of grouping together. So I don't know what the original names are. I don't know if clusters calls them particles. The video I watched this afternoon calls them particles. And I'm calling each like color like a family, but that's only like in the code. Like they sort of create animals or organisms. I guess it's like close to like how some kind of not squid. What's the word I'm looking for? These are like these sea animals that like create like colonies of different individuals. This is cool stuff. I like this. Okay, I'm gonna add just a button which like lets me regenerate. Yeah, with these settings, it does have like a bit of an organic feel to it, doesn't it? Like as they sort of like wobble and get close and jitter and stuff. And, oh, I love this. This is like it's rotating. I really want to find a way of like I'm not sure how to go about that, like algorithmically, like finding structures like this and getting the camera to sort of focus on it on its own. It actually looks like a fish, doesn't it? It's amazing. It's like there's a heart in the middle of the fish, and it's got these fins. Like there's a symmetry to it. Like it's got these two like eyes. I don't know. Maybe they're eyes. I don't know. Oh, there's still stuff happening down here as well. No, come back, come back. I want to see what's going on down there. No. This is cool. I'm having so much fun with this. Yeah, there's a bit of a, yeah, like there's something between like something happening in space and something happening in the sea, somewhere between those. This is cool. Come on. Like how? Wow, that was cool. Ah! I love it. Wow. Okay, I did not expect such interesting behavior. Like I expected something to come with this. but this is way better than what I was hoping for. Yeah, this one's really active. Oh wow! Look at it go! Oh, this is lovely. This is so cool. I just thought of a feature like a save this original condition, just basically like just dump a JSON of like the rules. Like it keeps like metamorphosing into like a different kind of animal, and then with all new behaviors. Like sometimes it's fast, sometimes it's turning, sometimes it's doing these sort of weird dances. Oh, I love it. Oh, wow. This is cool. Yeah, and so because of the average system, it's gonna like leave this, if it leaves the screen, like, yeah, so it's because there are too many particles at the bottom here, and then there are particles at the top. It's all gone. There we go. We've got a completely blank screen now. That was a real treat. Oh wow, I like that. I like that a lot. Let's go for one more, and then start like thinking about what we can do to improve this. Oop. Bye then. Yep, that's gone. Yeah, so we really need to like have some kind of way of like detecting where there are, well, I guess clusters are the right word, where there are clusters of like active particles, and sort of letting the camera sort of like maybe sort of swoop from one to the other, because it's a bit of a shame that we sort of lose them real quick. Another thing I want to do real quick, just to make things look nicer, is basically clamp that so I can stretch them, but they won't stretch infinitely. So velocity scale, and then public float max scale, and we're going to go math minimum of math f minimum of that maximum scale, and that, it's got a capital M. And so if I go ahead and put a nice value back here again, so max scale we can like go 2, what does a 2 look like? 2 looks something like this. Can we go to 3? No, 3 would be too much. 2's okay. Okay, so max scale is going to be 2, and we can go ahead and put this to like a higher value again, maybe 0.05. Let's see what happens with that. Yeah, so they squidge out a bit more. Go ahead and put those values a bit higher still. Oh, they don't squidge out. And also, in the editor, I think 250 is about the maximum we can get away with. Yeah, so now they sort of like scooch a bit more. Yeah, so we get these nice little movements. That's just a little visual thing. Someone mentioned, Yeah, someone mentioned trails. I'm not going to put trails in for two reasons. One, they can be quite costly, especially if there's so many. And the second is I think it'd be too much. I kind of want to keep things mostly simple. One thing I am going to do though, just to like add a little bit of mystery to the whole thing. Where's my lighting editor? Rendering lighting settings. Let's go ahead and put that there. What I'm going to do is go ahead and add some fog. So we don't want a skybox, we don't have a skybox. Ambient color, gray, yeah, sure, why not? Source, color. So there's no baked global illumination, there's no light mapping, that's all gone. Other settings, fog. I do want to add a little bit of fog, which is going to be the same color as the skybox color, which should be sure. Let's see what happens with that. We can actually tweak this while it's playing. Like the idea would be to like, oh wait, hang on. No, the fog should be like towards black. Yeah, I really wish they had like a proper way of editing this. Well, this could do like some interesting things with like having things sort of like appear and disappear into the background. I guess. I don't know. Might not do this actually. That's too dense. 1. We actually also want it to start at a certain point. Could we have, yeah, start and end. I guess it might be a bit an easy way to do it. 50 and like 150. Let's forget about fog for a minute. Adding camera weight to every particle did increase when in cluster. I mean, essentially that is what's going to happen, but to decide whether a particle is in a cluster... Oh, actually, I guess we do have that value, because what basically interesting things are happening when this attraction is maximized. So not the attraction itself, but the weight of the attraction. So this is the weight. And so what we can do is each particle can basically create its own weight on its update by sort of summing all of these. And that would give us the weight, I guess. Let's try that. Let's try that. So public float last weight. And so last weight on our update, it starts out by going last weight equals 0. And what we're going to do is we're going to go ahead and add that each time. So float weight of this particular direction is going to be that. Last weight plus equals that weight. There might be some like squaring or something because maybe something not interesting happens there. We're already doing the square root and a division, so we might as well reuse that immediately. And that weight can actually just be the weight, because when we come ahead and move it here, we're going to do this on the late update. It's going to be that multiplied by the particle's weight. So particle p equals that thing. So plus equals p transform position multiplied by p last weight. So that should do something. And oh, we need the total weights, not divide by that. We need to divide by the total weight. Float equals 0, and so Oh, actually, that was right. Actually, what I was doing. What did I do? Weight plus equals p last weight. And we're actually dividing by the total weight. Show the weight over here. And this should be less jittery. And if there's just a bit of jitter, we can just smooth the position. But I think it should be fine. Yeah, we got a bit of jitter, but we can smooth that in a minute. Actually, let's go ahead and smooth that now. Smooth that. Yeah, okay. Just smooth things. What effect do I want? Pretty much what I got, actually. I'm just trying to find ways to make things move in a nicer way. And also have the camera sort of follow what's going on. Wait, where are you going over there? That's not quite what I was expecting. What? What? Wait, hang on, can this be negative? No, because that's always positive. Oh yeah, it can be. So, math abs of weight. Oops. Wait, does it always need to be positive? Yes, it does. So actually the whole weight needs to be absolute. Because it doesn't matter if we're before or behind the position. So the what was going on. So this is my calculation I did earlier on. I was trying to calculate the weight. And so it's going to be negative on one side and positive on the other side. So I need it to be positive both ways, because otherwise what I'm getting is this graph instead. I'm getting that, and then like a discontinuity here, which actually might change the behavior of the full thing, but I'd rather keep things accurate. So this should always be positive. Let's go and see what that does. If you want to know what that graph is, you need to go back to the beginning of the stream. Okay, the weight thing might also be a problem because like here we have this situation where we have like a node that's sort of like very, very active on itself. But like if that's not necessarily interesting because they're always sort of staying together. I mean, I guess in this case it's kind of interesting, but we could have like a thing where something's like locked in a position, like just like a bunch of things are just like locked here and not moving, and then something like exciting is happening elsewhere, and it might completely ignore that. Yeah, smoothing works really well, especially like as soon as you have like jittery information like this. But yeah, so here we're like jittering, we're not smoothing. But you can just smooth things when it's like that. Okay, so let's go ahead and save that. Put ourselves back up to 400 particles and do a build and see what it looks like with the thing. Okay, so yeah, so for people who are dropping in and haven't been following from the beginning, which I mean I understand. Oh, this is a very sort of blobbity 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 thing. I'm going to go ahead and explain what's actually happening again, or at least what's supposed to be happening. So if you check in the video description, it actually sort of links to a video and also a web app of a 2D version of this, and I'm just making a 3D version of it. So essentially we have a world with a bunch of particles, and all of these particles like belong to families, and so each family is a different color. And what we're doing is each family has rules as to how it behaves with other families, and so there's a range, and when a particle of another family is in a specific range, it will either be pulled towards it or pushed away from it. And by doing this for every family, like having different rules for every family, we get these sort of interesting, complicated behaviors. This one's a fun one that looks like it's sort of swimming and pulsing forwards. So this is what's like interesting, because the rules are really simple. So like this yellow family here has a rule for like what range it wants to be of other yellow particles, or at least at what range it will push or pull. Same for the blue, this dark blue, same for the cyan, and same for these other two tones of blue. And it sort of does these, it creates these sort of like complex behaviors, because so the simplest example is like if we have two particles here of different families, and this one wants to move away from this particle, but this one wants to move towards that one, well, they'll sort of move, they'll drift through space like this. But then like if there's a third particle that wants to be close to this one but far away from that one, and this one wants to be close to this one, they will sort of rotate around each other. And then if you sort of add more complicated behaviors, interesting things happen. I like this one, this is cool. So the weighting works pretty well, because like it's ignored the particles that were over there because they're not interesting. But this is like an interesting thing happening here. So that way of weighting things actually works pretty well. Although so the others do have a weight, and so the actual like center point of the camera is like really far down that way, which is why this is getting closer and closer to the camera, because it's flying towards the camera, and the camera sort of aiming for a position like between this family here and between the ones that we've forgotten behind. It's just that it's much more drawn to this family than it is to the others. This is a really interesting movement though. Let's go ahead and reset, and let's have a look at some other interesting behaviors. Okay, I'd like to avoid this kind of stuff if possible, because it's not very nice to look at when they just get glitchy like this. Might have something to do with the radius thing, and we can probably just like add a radius to 0. Like I don't know if things actually need to have like a bump radius or not. We're getting lots of spaceships here. And as these are sort of like dropping off sometimes, I wonder if we'll lose more. It's particles, baby! It's living particles, it's particle life. Yeah. we had a really beautiful organism. I'm assuming I'm going to go ahead and find the recording and and try and find that one because that was a really beautiful one. I was amazed at what we got. Yeah, I'd like to avoid these sort of like too tight clusters that just get too excited. I like it when things are like swoopier. I don't like things when they're vibrating. Like I don't mind like this sort of like an aggressive sort of like moving around, but when it's just like, it's not very nice. I don't like it. Oh, yeah. Oh. Ah, see, this is the kind of movement I like. They're sort of swooping around each other and interesting things happen. Nice. Okay. Is that the end of that, or are we going to get some more interesting things happening if these sort of getting close or something? I think it's essentially random because there are like integration steps. So basically, like things in real life move continuously, but in a computer program they're moving like step, 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 step. And so if we have like two things that are like attracted to each other, um, in real life they sort of go bounce like this. But if they're moving like too close, too fast in a simulation, they might just swap positions and then swap positions again, swap position. But they might like not swap position the exact same amount. So if essentially we're just getting like a random sort of behavior, which I mean, like it's similar to like these two things, sort of like going whoa, like really fast, but they're sort of like clipping through each other, which I'm not a big fan of. And I'd like to avoid like vibratey kind of movements, if at all possible. I could also like smooth the velocity of the particles as well. Like that's a thing I could do. Yeah, there's gonna be like interesting like kind of behaviors like that, like electron orbitals, planets, and sometimes like it moves like a bit like a fish or something. Um, yeah, there's a bunch of interesting behaviors happening. Ah, this is one of the exciting ones. So this kind of movement here, like where they go like wiggle wiggle like this, it's basically like they're being attracted by one of the groups, but then repelled by the other, and so they'll sort of like get close enough to the group that repels them, and then sort of like push out, and then they sort of get stuck in sort of like this area where they're simultaneously being pushed by one group and repelled by the other, and it sort of creates these sort of like shells. I think this is what these shells we're looking at are. Yeah, I like this. The new sort of like cluster finder system is working pretty well, because like it wouldn't have followed this group quite as well as before. But I do think that I'd like to find a way that sort of like finds groups. That way the camera could sort of like move from one group to another and sort of like show us different things happening at different places in the world. But for now, this is doing pretty well. This is where I was leaving it, because when an organism sort of gets close to other organisms, that's when exciting things happen. What happened? It split apart or something? Yeah, it looks like there's an organism that's like way like behind the camera, causing the whole thing to zoom out, because we've got one exciting organism over there and one exciting organism like here, and so the camera doesn't know where to be, so it's like between them. Cool stuff there. So that previous case where we had like two interesting groups, the camera doesn't know which one to pick, so it's kind of picking between. We're back to the same problem as before, where like trying to pick the average interest position means that if there are two interesting positions, then we don't know which one to go to. And I'd like to be able to sort of like find the density of interest and then like have the camera sort of like move between those like dense areas. I think the metric of what counts as like an interesting particle is good. Okay, so I think what I'm going to do right now is add a button which lets me randomize the rules. So one button for randomize the rules, one button for like just respawn a bunch. So this is the spawn thing. So basically just like delete all the particles, respawn a bunch. Another one that will randomize the rules, so we'll do this, just like reset this. And then another one which will actually respawn the rules, should be like all of that. And then another button to just like reload everything, just re-roll everything. Okay, so let's go void roll rules. So roll rules, what it's going to do is it's going to do one of these. So take each family, go ahead and create a new rule, and then the rule for the ith. Yeah, so we need to reset that though as well. Actually, no, we don't. Yeah, cool. So this is roll rules. Okay, this creates new families, and if we create new families, as long as we have the same family count, we don't need to re-roll the rules. So let's go ahead and go void create families. Wait, creating new families is re-rolling the rules. That's the same thing. So the only reason we need to do this is if we have a new number of families. So that's fine, we don't need to do that. This, however, should go in the spawn particles. Let's call it do spawn. So that does that, and also real quick, if particles different to null, and particles, well, actually, for each particle P in particles, destroy P game object, and then create a new set of particles. And this is do spawn. Cool. Check if that works. It does. And now void update. If inputs gets key down of key code R, we're going to roll rules. Key code T, we're going to do spawn, and Y do both. Yep, see you around. Take care. So let's go ahead and check that out. So roll new rules. So right now I can like change what the rules are at any given time. Then I can respawn. Okay. That's because we're dividing by 0. Did I? Yeah, okay. So roll new rules, respawn the particles, cool. And then new rules, new particles. Wait. We should get it to re-roll the colors as well, right? If it's new rules, it should be new colors. It's not actually doing that. Okay, so we need to do this the old way as well. So it's going to be one of these. J, family, familam equals families J. So familam color 2. And at the end, families J equals familam. Rolling the rules is not changing. Oh, it also needs to reset the colors as well. So once it's done that, basically call void start on each particle. That should work. New rules. New rules. So the particles stay the same color. So wait, I want us to find a group of particles. Okay, so do all these purples like stay? No, yeah. So whenever I roll new rules, it reassigns. So I don't want to do that actually. So yeah, we don't p in it on a roll rules. They should stay the same color. Not sure how to deal with this situation. Okay, so we are getting in like interesting behavior from just resetting. So if I hit Y a couple times, I'm going to put some music on because I'm getting a bit bored of silence. I am now going to play a different album. I'm going to play. What am I going to play? Yeah, let's go for some. Some of that stuff. I am now listening to this. So now if I respawn, I get new interesting behaviors, like each time I respawn. Is it the same colors? No, it's different colors, isn't it? Is it? Yeah, it's different colors. And so what I can also do is I can respawn particles with the same rules, which should give us like more or less the same behavior each time. Or I can just reset the rules now with the particles wherever they are. That's actually kind of cool. Problem is there's too scattered now. So if I do that too often, then eventually like this, they're all just scattered around in space. Got another one of these pulse swimmers. what happens if I switch the rules? Change direction. Form. Turbo speed. Switch the rules. Okay, switching the rules, you do get some interesting things happening. That's a cool one. And switch the rules. Switch again because, yeah, no, everything's just sort of spread out. This is cool. And so, oh, I didn't switch the rules this time. I did that on its own. So switch the rules. That was a switch the rule. And respawn them. I'm really happy with this. Some really interesting dynamic behaviors. Oh, another cool thing would be is to like find a way of generating sound based on like where they are. That would be cool. So yeah, I'm gonna do something about these sort of like glitchy things here. I think what I can do is gonna go ahead and add a new parameter to particles, which is gonna be vector3 acceleration and a public float smooth velocity. And what I'm going to do is, so the spawn particle is going to have a new value here, which is going to be the smooth velocity, public float smooth velocity, should be equal to like 0.1, I think. We want something pretty quick. And velocity is going to... Yeah, so transform position is going to be... No, we want to smooth the velocity itself. Yeah, so instead of moving the velocity, I'm going to go vector 3, 0, sorry, vector 3 excel equals 0. I'm getting tired, I think. I'll do this bit and then call it a day. Velocity delta. So we change the velocity delta. Do that outside of the loop. And after the loop, velocity is equal to vector 3 smooth damp velocity. Velocity plus velocity delta ref smooth velocity. Sorry, acceleration, smooth velocity. That should work. Yeah, the thing is with the audio, it's going to be really difficult because like it's more of that trying to like figure out what's interesting things are happening, when they're happening. And I don't know. I'll see. I'll figure that out. Oh yeah, with 400 it gets slow, doesn't it? Spawner 200. Let's go and see what happens here. Yeah, things like move a bit more stably. If you have a smooth velocity of, we're not actually setting smooth velocity, it's not doing anything. I am stupid. When we spawn the particles, one of the things we want to do is go to P smooth velocity equals smooth velocity. Otherwise it's equal to 0. Not quite doing what I was hoping it to do. So if that's equal to 0, it works. Like it's doing things. Like this is doing the same thing as it usually does because I set the smooth velocity to 0. But as soon as I set it to anything, things just like stop doing anything. I mean, they do something, but it's became more sluggish. I don't think it's doing... Yeah, it's not doing what I want it to do. Yep, screw that, that's not interesting. I wonder if I should randomize the frictions. Like each family has its own friction. I think I'm going to call it quits for now. I don't think I'll do the rest on stream. That was just fun to like do here and now. Maybe I'll do the rest on stream, but like usually when this kind of project I like to just like jam it out whenever. But this does lead to some interesting interesting behaviors at least. Okay, yeah, I do need a bit more friction than that. Although that's exciting as well. Can reset it back to the friction I had before, which was 10, I believe. But we can have some fun, like changing these friction values to get some interesting behaviors. And also I need to turn it into a screensaver too. This could probably be shaderified as well. I don't know, maybe, not sure. This is lovely. I'm really enjoying this. I'm gonna play with this more. I really want to find a way to get rid of those vibrations. I guess doing better integration, probably. Yep. So, I'm going to call that the end of this stream. Because I got something, and from now it's going to be like tweaking and optimizing and trying to figure stuff out. So like the main interesting bit was like coding the beginning of this behavior here and getting something interesting out of that. Which like is done mostly. It's funny how like rule changes sort of like sometimes creates a fish and just like dumps the rest of the fish in the middle of nowhere. Yeah. So yeah, so on that, I'm gonna call this one quits. I'm gonna post this code up to my repo. I don't think there are that many people in chat, so most of you already know where my repo is. And you know where my Twitter is as well, anyway. I don't know who's watching. I don't, I guess. Yeah, so I'll post the... Oh, it's because the page is scrolled down. There you go. Oh, it's just me now anyway. Yeah, so I'll post everything to my repo and the stream here, and see you all around. Yeah, that was fun.